Yeah, yes, sir. I just wanted something to keep me going. Yeah. Recording here. And that.
No, it's okay.
That. Yeah, I was doing the wrong things, really. I know what I was doing. So now now you're seeing both, eh?
Yes.
So now this is month now. I'm dealing with here. I'm generating data for advertisement cost and accompanying sales volume, and we go on up to there. Say those many months, eh? This the advertisement. Say this is the advert cost is X. This say is 12 in millions of shillings, 34, 56. I'm generating some numbers here, eh? And then say then 12, and then 34, and then 56 again, and then say 70, and then say 21, 30, 24, 54, 34, 24. Those are the advert costs. Accompanying sales volume, why? Why I'm going to tweak this data again? I'm just tweaking it anyway. So usually this is 40, and then this one say is also a 45, and then say again here is 46. Then go on and on and on. Say 48. There's something I'm doing here. Don't worry. Then you go down here. You get that. You get that. That is say. So say this is 60. And then here we have here is 34. This one here is 32. That one here is 36. And that one here is 38. Then go on and on. Let's say 30. And then of course 30. Then say 28. And then say here 28 again. And say 23. And say 15. These are the those are the sales revenue generated from X when you advertise in X. Then we used Carl Pearson's to get the correlation here. We are not going to go there because you have done that. We did that last time, both using the model and using SPSS. So I mean Excel. Today I'm going to deal with ranking. You want to rank this. No, sorry. If you want to look at the effect of sales volume, the effect of advert cost on sales volume, you can collect data in two ways. You can go to the organization and go to their records and just pick these things here. They are here per month. Or you can go the primary data way. Then you ask respondents, probably the head of that department. You ask them questions on sales volume and advertisement costs. So and then you ask them, you ask, say, suppose this one you're asking over, suppose this not be months, let this be organizations. So you select 13 organizations so that the next example makes sense to you. So you go to these organizations, you pick this is what they spend, this is what they get. What they spend, that's what they get. The third one, spend, get, etc., etc. Or alternatively, you go to this organization and ask them to rate the level of their advertisement costs on a scale of 1 to 5, where 1 is too low, 2 is low, 3 is average, 4 is high, 5 is very high. You ask them. In the same breath, you're also asking them to rate the significance of the effect of sales volume the significance of the advertisement cost on sales volume. Again, on a scale of 1 to 5, they'll tell you very significantly, not at all, significantly, moderately, very significantly, blah, 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 and extremely significant. So what you do then, you go to, so this is that's the second more way of collecting data. So let's say this is sales volume rating. This now rating, not X, but rating of X. Just call it rating here, rating. And this one again is rating of X. Say rating of X. I'll tell you how that comes up. Rating of X. And then this is the rating of Y. Rating of Y. So you have rating of X and rating of Y. So suppose this one gives you 1 and this one rates 4. This one gives, let me just give you my numbers here. 1, 2, 1, 4, 5, 1, 2, 1, 3, 4, 5, 5, 1, 1, 2. That is it. Then they give you this. I'll just tell you, I'll just tweak these ones again. I'm tweaking them. So this one say 4, and then this one say 3, and this one then say 4 again, and this one say 4, 3, and this one just say 2, 1, then 2, then 2, then 1, sorry, 2, whatever, and then 3, and then 3. So these ones here are ratings. So if you were to get correlation between the rating here and the rating here, the best coefficient you should use is Charles Spearman's rank correlation coefficient. These are already ranks, so you don't have to re-rank them. Likert scale itself is a rank. That's why it's called order. So these are already order. So this is one way of collecting data. Similarly, this is the second way. Third way is using the actual values, the scale variables. The other one is using ordinal. But suppose you collected this data, but want to use Charles Spearman's to get correlation. You cannot use the data as collected. You must rank them in ascending value of H, ascending value of X. Ascending means the highest value is number 1, the next is number 2, the third is number 3, the fourth, just like you normally give marks to students, but there's a variation. So you need to create a rank here. So I'm going to leave this. This one is no problem. You calculate Charles Spearman's direct, and that is easy. And this is the reality, incidentally, and this one. So what do? I come here. To do this, you must recognize 2 options, very critical. To create ranks from scale variables, you need to recognize 2 options that are available to you. The first option is the rank when values are repeated. Values of each variable are repeated. You look at whether they are any one of them repeated, either X or Y, use a different model. So in this model here, which values are repeated here? Just tell which values are repeated here. Here, tell me the values repeated. Just give me 1 or 2.
34.
Eh?
34.
34.
12.
56. 12.
12.
Beautiful. So you must just identify that one first. As long as one variable has repeated values, they don't have to be both. Then you use a different model. But you also have a case where these values are not repeated. And I'll go there. Where there is no repetition at all. So I'll go there. Suppose I have the same data set, but now there is no repetition at all. Where there is repetition, I can change this one to 36. This one I can leave it 34. Is there another 34 anywhere? I can this one to 33. Is there any 34 somewhere? I can change this one to 30. Any 56 here? I leave that as 56. 30, I'll just make this one 31. Then what is this, 56? This 56. Then 56 again. I can make this one 55 and this one say 54. Any other repeated here? 12, 11, And then any other repeated here? None. Fine? Here.
Yep.
Then I come this side. Any repeated value here? Any?
28.
28. 28, I can make it 27 here. Any other? None, isn't it? So these are different ranking options. So I'll start off with the easiest, this one. I'll label this one R of X, is subscript, The rank of X, rank of X. We call it R of X, subscripted, Rank of X is that. And then I need my rank of Y. Rank of Y. Again, subscripted. Rank of Y subscripted is here. There we. And we read in ascending order of ranks. So you start with X. What's the highest value?
70.
What's the highest value?
70.
Number 1. The next highest value?
56.
Number 2. The other one?
55.
Number 3.
55.
Please listen to what I'm doing very critically because problems will emerge in a few minutes. Next?
54.
54.
54. Where's 54? 54 is up here. Number 4. Next?
36.
36 is number 5. Next?
34.
34 is number 6. Next?
33.
31.
24. 33.
33.
33.
33 number 7. Next?
7.
30.
30 number
1.
31. 31.
1 is number 8.
8.
Then 30, 9.
9.
Then
24.
24, number 10.
10.
Then
21.
number 11. Then
11.
12.
number 12. Then
11.
number 12. Then 11. Those are the ranks. Just like
Number 13. Number 13, not 11.
number 13, yes. Number 13. Those are the ranks. It's just like assigning numbers to students in an examination. I mean, in primary. Yeah? It's the same thing. The same thing. There's no difference. Then come this side. Come this side. What is the highest here?
60.
Number 1. Next. Number 2. Next.
46.
Number 3. Next.
45.
35, Or 36?
45.
45.
45. Where is 45? Here.
Yeah.
Number 4. Next.
46.
46 number.
Oh,
So this is actually number 3, This is actually number 45. 46 again.
45 is 6.
This number.
30,
This number 1.
38.
38 is number what?
26.
5. Number 6 is?
36.
36.
36.
36 is number 6. Then
34.
34.
34 is number what? Where is 34?
11.
34
Number
is
12.
number 7. 34 is number 7, yes? That one,
32.
Then
32.
32.
32 is number 8.
8.
Then
30.
30.
30 number 9. Then
9.
28.
27.
8.
28 is number
10.
10. Then
7.
27. 11.
27 is number
11.
11. Then
23.
pardon?
23.
Number
12.
12.
12. Then?
13.
13.
Is that okay? But you see, even there by a casual look, casually, you can see these variables are positively correlated. Aren't you seeing the ranks are almost the same?
Yes.
5, 5, 12, 13, 13,
Yes.
12, 9, 9. Those are positively correlated, just casually. But let's not deal with that for now. So this is okay. How do you confirm these are the correct ranks? You add them. If you have done the correct ranking, this is mathematical theory. You add them. You add them, and then get what you want to get. Just a minute. Come on, please. You add them this way. Your normal adding. Come here, and I add them. Sum them. They should be equal. Are you seeing this? Okay?
Yes.
Sigma r of x must be equal to sigma r of y. If there's a difference, you have got wrong ranks. You must always do that. There's a mathematical relationship. That ensures there's a mathematical background to this. That for proving that the two ranks are equal. So you always need to do that. So this is okay. Now you can see these ranks here is just like Likert scale, isn't it? Is there a difference? This is Likert scale, isn't it? But this is also ordered, isn't it? So you have converted your scale variables into ordinal. Ordinal. This is like number 1, number 2, number 3, number 4, blah, 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 up to number 13, etc., etc. Now let's come here. Where values are repeated. Any one of the variables having repeated values is enough. So I come here, here, here. And then I deal with now with the ranking. Give me the first one. What's the highest under X?
70.
How many are there?
1.
1. 70 is number 1. What's the next highest?
56.
56. How many are there?
3.
3.
3.
Good. So what is the rank of 56?
3.
What's the rank of 56?
3.
2.
3 plus 4 plus 5 divided by 3.
Why? Why?
To ensure we rank until number 13.
No, that cannot be. That cannot be. Anyway, any other point of view?
2.
2.
2.
Huh?
2. 2, 2, 2.
2.
Yes.
Then
Two,
we
two.
skip.
Then we skip.
4.
We skip
We
3.
skip 3, 4.
Skip 3, then we go to. Is that skipping
5.
bit where I wanted to?
4.
Now, so this is the bottom line. It's only him who is correct actually. Here you don't rank as if you are ranking primary school children performance in an exam. People don't share ranks. You know, even in primary, if you have 90, 90, 90, you are given 1, 1, 1, isn't it? Then the other one is given 3, isn't it?
Yeah.
Which should never be. Should never be. But you know, parents will not understand if I gave your child number 1.5. You know, number 1.5 because they shared. Because both of you cannot be number 1. You should have been given the average of what you have shared. That would have been the best measure, not the actual one. Then you jump the other one. You're getting what I'm saying here. Eh? There must be a representative rank for all the 3, and the representative rank for all the 3 cannot be 1. It must be the average of the 3 ranks. Eh? The one. So this is how you do it. And note this: that if a value has repeated ranks, if a variable has repeated values, if a variable has repeated values, then assign them a rank. Then assign them a rank which is equal to the arithmetic mean of the ranks the repeated values would have been assigned. Assigned them the arithmetic mean of the ranks the repeated values would have been assigned if there was no repetition. You assign them a rank which is equal to the arithmetic mean of the ranks they would have been assigned if there was no repetition. So if there was no repetition, they would have been assigned some ranks. So you get the arithmetic mean of those ranks they would have been assigned. So in this case, number 70 is number 1. 56 is the next value. If there was no, and there are 3. If there was no repetition, we would have given them rank 3, 2, 3, and what? And what?
4.
And 4. Then you get the arithmetic mean of these ones. So what's the arithmetic mean of these ones? You add this, divide by what?
3.
By 3. So what is 7 plus 2? 9 plus 2 is what? Sorry, 7 plus 2 is 9. 9 plus, divide by 3?
3.
3. So 56, not where you are. You are on rank for number 4, isn't it? You must always note that. So now you are where? So this now therefore is rank 3. Where's the other one? Where's the other 56? Rank 3. The other 56 is where? Rank 3. Now you're on which rank?
Rank 5.
5.
Rank 5. Should go to which one? What's the next highest value?
34.
34. How many are they?
3.
3.
4.
3.
4.
There
There are 4.
There are 4. So which ranks would you have assigned them if there was no repetition?
5, 6, 7, 8.
Which ranks?
5,
5,
6,
6, 7, 8.
5, 6, 6, 7, up to what? 8.
8.
That's what you'd have. What's the total there? 15 plus 5, 26, isn't it? 26?
Plus 6. 15 plus 11.
Is what?
26. Okay.
26 divided by 4? 6 point what? 6.5. So this rank is 6.5. This other, where's the other 34? 6.5. Another 34 is where? 6.5. Another 34 is where? 6.5. Next, what's the next value? The next highest value is what?
30.
How many are there?
1.
Number 9. Next one. How many are there?
1.
How many is it? Oh, what's the next highest value?
24.
How many are there?
1.
10. Next highest value?
21.
How many are there? 11. Then?
212.
Go 12. 12 plus 12?
24.
12
Divided by
plus
2?
12.
12. So this is 12 and that's 12. That's why
It's 12.5.
it's 12 and 13, It's 12.5.
Yeah.
Good. And then this is also 12 point what? 5. So you see the notion that they need to go up to 13 is not right. You're getting me now,
Yes.
Yes. The whole idea is that you sign a representative rank if the ranks are shared. That's the notion, and that's the logic. Let's now rank 8. Why? Let's go to why. Why? Let's rank. Is there a repeated value in y? The highest one is what here? 60, isn't it?
Yes.
Number 1. The next one is what? 40?
56.
56, how many are there?
56.
48.
Why?
Where's 56?
No, sorry, I was checking the X. Sorry.
This is 2. Next?
46.
46 are how many? 3.
1.
Eh? 1.
Number 45 is how many?
1.
1.
Next is what? Next is 38.
38.
Yes.
How many are they?
1.
5. Next is 36. 36 are how many?
6.
6.
Just one.
Next is what? 32. 32 are how many? 7. Next?
7.
It was that. Okay.
34.
34.
There's 34.
34.
34 is 7. And therefore, there's no war here. Eh? You know, there's no war. There's no war. 32 is what? 8.
8.
30?
9.
9. 28?
Yeah, 2.
10 plus 11, isn't it? 10 plus 11, eh?
10.5.
10.5.
10.5. 10.5. And then 10.5. So, where are we? 12 now, eh? 12 is that. And then this is what? 13. And we are done. How do you confirm these are correct ranks? You add them. You add them. And they need to be equal. 91, 91. You see, for the same data sets, the ranks will be the same total. This is 13. There's a reason why. I can tell you the reason why. The reason why. But I don't want to go to the mathematics behind this. Eh? So this is correct. So this is the first step towards dealing with Charles Spearman's rank correlation coefficient. Then step 2, after ranking, we now determine rho, Charles Spearman's rank correlation coefficient. But let me ask you a question. Which of these 3 scenarios of ranks is reality? Which ones are reality? Here. Just, I see I'm pointing and there are 3, eh? This one, isn't it? And this one, and this one. Which is the reality? Tell me which is the reality. Which you'll get in reality.
First one.
Repeated.
Repeated. This is theory. In fact, this is theory. This one is theory. So you need repeated, and repeated are these 2, isn't it? Aren't you seeing 2? These ranks are repeated here. Aren't you seeing this? Eh? There's 4, 4. There's 5, 5. Are you seeing this? Eh?
Mm-hmm.
This is the reality, incidentally. This is theory. This one is theory. That's what I want you to identify first. Now, how then do we determine Charles Spearman's? We determine Charles Spearman's recognizing either repeated ranks or non-repeated ranks. Ranks for repeated values or ranks for non-repeated values. So I'll start with the theory, this one. The model for determining rho when the values are not repeated. Very easy. And I'll give you the model here. I'll give you the model here for determining rho when ranks are not repeated. And this is the model. There's an error in your presentation, which I'm going to tell you to correct. But don't worry, I'll deal with that in a minute. In a minute, I'll tell you what that entails. What the error is about. Let's come here first. So this is the model. I'll put it here. This is the model for this scenario, this scenario here, this scenario. Where is the model? This one. So what does this model tell you? Rho is here. So you want to determine D, where D is the difference between the ranks. So I determine D, which is equal to R of X minus R of Y. It doesn't matter which one you subtract from which. Why? Because you're going to square them, aren't you?
Yes.
Yes. So I come here and I'll do that just now. In fact, I'll square this rather than wasting time with a lot of steps. I'll square this. Just come here and square this because you need to square this as per the model. Squared. And then here, also squared. So I come here and determine my D squared. My D squared. Here. This squared is basically bracket this minus that bracket whole squared. And that is it. And then what do you do with the D squareds? What do you do with them? You sum them. And I'll sum them here. That is the sum. 6. What do you do then? You substitute. What is n here? What is n? What is n here?
13.
13. So our row is equal to 6. I'll tell you this. I'll just do this. It's equal to 6 times. 6 times what? Times this. That's the sum, 6 times this. Divide by what? Come on, sorry.
13.
Sorry, just a minute, please. It is 6 times that. 6 times F30. Yes. Divided by 13 squared. 13. What is 13 squared?
269.
What is 13 squared?
269.
13 squared?
169.
169 minus 7 minus 1.
168.
168. I'm just trying to solve this. So it's 13 times 168. That is that. Sorry, I need to put an equal sign. And that is that. And then we do that with that expression. What do you do with that expression?
You subtract from 1.
You subtract from 1. 1 minus this. What is it? What is the value?
0.98.
0.98. Strongly positively correlated. If we did Carl Pearson's, we will not get the same value, but we'll get the same, we'll draw the same conclusion. We'll not get the same value, but we will draw the same conclusion. In fact, the difference may not be significant. But that is for this. You use this model. Am I clear, please?
Yes.
And this is the model I've used in your presentation, whether ranks are repeated or not. That is wrong. So where you found me, I've used this one here. Even for this case, ignore this model. That is wrong. You go and change it. You go and change it. And then you use the model I'm going to give you, where the ranks are repeated, both for this and for this. So this is the model where ranks are repeated. So note, just note in your notebook there, that Charles Spearman's value, where values are repeated, is determined using an adapted Carl Pearson's. Is determined using an adapted Carl Pearson's correlation coefficient. An adapted Carl Pearson's correlation coefficient. Adapted, not adopted. You don't adopt it. You adapt it. And how do you adapt it? You adapt it this way. So I'll get you the model we used last week, and that's why I told you to use that model. You can even use the other one, but I'll give you the one that so that we are clear. I'll give you the complicated one so that you can use the easier one out. Adapted. So we adapt this model. This is the model we adapt. That one. This is what you adapt. I'll make it smaller so that you see it. We adapt this. Hii ndio tuta-adapt hii. Let me just make it smaller. Then you see what it looks like. That is it. So we are going to adapt this for the case where ranks are repeated. Where ranks are repeated. How do we adapt it? Where there is X here, you put R of X. Where there is Y, you put R of Y. That's the adaptation I'm talking about. So in this case, since this is our model, I'm going to change our problem is that when I'm on sharing, this thing does not do what I want it to do. It gives me other things. Other things, because now it's very small. You can't see. You can't see it anyway. So that it doesn't work that way. But I'll tell you what to do. I'll tell you what to do. Don't worry. I'll tell you what to do. Just in a minute. I'll tell you what you do in your notebook there. How we adapt. Let me just undo this thing here completely. Get off here. I'll repaste it here. I'll bring it up here. So this is, let me just put it large here. So this is the row. So change this to row. Row, write this one here, this one. Row equals to, let's write the numerator. N sigma R of X. You're seeing this R of X here, this one, This one. Place it where X is here, times R of Y. Just write R of X, R of Y. Minus sigma, what is here? Where I'm pointing? R of X. And here?
R of Y.
R of Y. Over the square root of big bracket N into, there's a bracket here, sigma, what is here?
R of X squared.
R of X squared bracket minus bracket sigma, what is here?
R of X.
The sum of R of X, then big bracket, squared, then big bracket, times big bracket for Y now, N into sigma R of Y squared, bracket minus bracket, the sum of R of Y squared squared. So R of Y squared, bracket. That is the adaptation I'm talking about. That is the model in reality. Because reality has repeated values. And that's the model you need to be using to determine the rank correlation coefficient. So it is this one here. So I'll use this. So here, I need what here? Look at this. I need what? R of X times R of Y. So you need a column here, R of X times R of Y. I'm not going to be bothered about the subscript. You know what I mean, So where is that? R of X times R of Y, this times that. That's the column. And I do it everywhere. What do I do with it? I sum them. Are you seeing this? Sum them. They are here. The sum of R of X times R of Y. Then I also need sigma R of X, it is here. Sigma R of Y, it is here. I don't have to read again. Then I also need R of X squared column. R of X squared. Where is squared? Squared column. Where is R of X? It is this one. Squared. And that is it. And what do you do with that? You sum them. You sum them. It's here. The other one we have this one here. So we don't have to recalculate it again. It's already here. Sigma R of X. And then I also need R of Y squared. Where is R of Y squared? It is here. Then we just copy that. Is that. And that is it. And here. What do we do with this? We add them. I add them. Added. That's it. That is R of X, R of Y squared. Now this one is here, so you don't have to bother about it again. So what do? I simply come and now substitute into my formula, my model. The first one is here, n times R of X. Where's n times R of X? Where's n? What is n here? 13. 13 times what? R of X. Where's R of X? Sigma R of X. This one. The other one is what? I'm just calculating them there. The other one is what? A sigma R of X times that is 91 times 91. So this one is times 13, eh? Yeah, it's there, times 13. What do? I get the difference. Next, I go to the denominator. The denominator is the sum of R of X squared. Where's the sum of R of X squared? Times n. N is 13 times the sum of R of X squared. Where is that? It is this one. Minus the sum of that squared. Where is that squared? It is this one. What do we do with this? We subtract them, don't we? This, sorry. That minus that, you get that. So I've gotten the X part. I do the Y part, which again is 13 times. 13 times what? 13 times what? R of Y squared. Where is R of Y squared? This one. No, sorry. This one. Times the other one squared. The other one squared is the same. The same. You don't have to bother. It's the same. No, that's not right. I just do it anyway. Anyway, well, let me just take this here. What do I do with them? I do what with them? I subtract. Fine? What do I do with those differences? What do I do with them?
Multiply.
Multiply them. After multiplying, what do I do with the multiplication?
Square root.
Square root.
Square root. I'm doing that at the same point, 0.5. That is it. What do I do with that now? The result.
Right.
I divide the numerator by what? By this. And give you a 0.98, isn't it? This is what we predicted, that these ranks are very close to each other, positively correlated. Is that okay? Fine?
Yes.
So this one here is R of X, and this is R of Y. I just do this here. I come here like this. I sum this the same way. I copy this quagmire here, everywhere, and I paste it here, and I paste it here, paste it there, and then I come across here. So these are my values. These are my values. So this one here, this one's here, I just bring them here. These are the things I'm talking about. I just bring them here. These are the ones. I'm just going so that I don't have to calculate these things. Those are the values. So you can see, these are the values, 36, 36. Of course, this is the same as that. 112, 112, that is that, 61. Of course, they're 13. And they 13, are they? This is 13. Yeah, they're 13. So this is 61%. This one based on Likert scale. Again, strongly positively correlated. This there. So this is Charles Spearman's. Any question, please? Any questions quickly? Good. Good. Look at this. I want to do something here for you. Excel does not have this capacity of Charles Spearman's, but let me just calculate this using Excel, the data. the data, this one, you see what happens, Excel, this analysis tool pack, come here, come here.
Excuse me, sir. There's a portion on your screen that is dark. Or is it only on my side?
You know me, darkness, I can't remove. That's for a fact, my sister. Darkness. Where? there's nothing which is dark here. I'm also in the darkness. Do you have power?
On our side, there's something.
Are you okay? Are you okay now? Are you okay now? Are you okay?
No, what I mean is there's something
No.
obstructing.
Anyway, don't worry. If there's darkness, that one is survival for the fittest now. Where are you staying? Because you may be staying in now a place where it's darkness now. So these are the ranks. These are the ranks. I just want to show you something here. These are the ranks, And then, of course, the labels are in the first output. The rest of the things you leave as is. And in the column, I run this. Look at what I've gotten. 0.997. You see this, Are you seeing this? Are you seeing the value?
Yes.
Yes.
Is it different from this one? This one?
No.
Is it different?
No.
No. If I use the ranks. But if I used this, then of course you can use it and you can check yourselves. That's the beauty with this Charles Spearman'S and Carl Pearson's thing. It tells you that it doesn't matter which one you use, incidentally. You will get non-significant difference between the values because your conclusion will be the same, literally the same. Am I done with that, please? Quickly, very quickly, in 1 minute only. Only in 1 minute, you do for me the following. This is X. X. This is Y. I'll give you the values here. 23, 56, 70. And then of course 12. And then I say is 34, and then 34, 56, 43, 23, and then say 50. Those are my two values, Two values of X. I'm going back there, don't worry. I'm going back there. I'm going back there. This is it. These are X and Y, X and Y. Casually, which of these models are you going to use?
Second one for repeated.
Second one for repeated. So do that quickly. And R of X here. Quickly, please. R of X and R of Y. And calculate. These are just 5. How many values are they? You need a column here. 1, 2, 3, 4, 5. Tafadhali, 5 minutes. I'm hearing you using Excel there. I wish you use your calculator. I wish you could calculate, and you can still use Excel to do calculation, but you never know. What's the value? Where's the value?
0.987.
0.987.
7.
Anybody with something different? Anybody with something different?
It's not finished.
Not finished.
Yeah. Always try to finish quickly. And life will be very easy. Yeah. Want to see. Good. You done, eh? Anybody with a different answer?
I got 0.625.
0.625. 0.625. Anybody else?
Negative 0.6689.
Is the correct answer, isn't it? That's the correct answer. And these are the ranks. You got this?
Yes.
They are here.
Yes.
The rest, you know the drill.
Repeat the answer.
What did you get? The answer, the correct answer?
Negative 0.6689.
That's it. Approximately. So they are negatively correlated. And that is it.
Question.
Yes.
When you calculate with Excel, it gives a different answer.
It doesn't, I can tell you. Which answer? What did you get?
I think the correct one is the 6.6689, but with Excel, I'm getting negative 0.6879.
That is it. That's the answer. Excel can never be wrong. It's only you. You know, Excel, this one, I've got the same, incidentally, yeah? This one. Of course, if you're rounding, but there's no rounding here. You know, there's no rounding here. I want you to implement this. What I want you to just confirm it is minus 0.66 or even 67 something, depending on your accuracy, yeah? If you round, eh? So if you get this correctly, then this is what I've done. I'll show you what I've done, eh? What I've done is here, I come here, this is that, then I highlight everything here. That's it. As long as these ranks are okay, yeah? Of course, by column, label, and then I calculate. This is the correct answer. negative 0.667. Is that one?
Yes.
And that's what she got, eh?
Agreed. I used the XY instead of rank of X. And
Yeah, I had you tapping Excel. I had you tapping. That's what I was saying. Don't tap that thing. You know, I had you, my brother. I did, Jackson. Don't worry. See, you had me tell you that I'm hearing you tapping something. That is the challenge of tapping things here. So, in the future, just listen to me quietly because I know what you are doing behind the scenes. Eh? That's why they behave like that. But that's it. Excel cannot be wrong. It's you who can be wrong. Eh? You know, it's garbage in, garbage out. Eh?
So in an exam, you can use any method, Excel, or you go the data way.
I don't go to the exam. I mean, you know, now you know how exams are done, isn't it? Mm-hmm. You know, these exams have instructions. Read the instructions. You know, in some way, I just sympathize with you as a human being. Eh? This man has used Excel. Did he actually read the instructions really? Did he read? Then in my mind, I think that this one, if you penalize this one, may collapse, you know. So read the instructions. That's where there's a reason why those instructions are given. Don't enjoy things that you have not been told to enjoy. Anyway, let me keep quiet. That's why sometimes we post instructions, even in fact, I'll post the instructions a week earlier so that you continue reading them on your cell phone.
Please do.
And I will. But why should I? These things you have, there's nothing going to change anyway. But I will do. I will post instructions early. So now if you do things that are not there, you know, you are told to submit in some way, then you submit. Where's Kanye? Where's Kanye? Kanye doesn't belong here.
I'm here.
Yes, he submits them. He submits them elsewhere. You know what I mean? Then I don't go there because I didn't tell you to go there. Then this thing delays inside there. You tell me now I don't have my results. Where are they? You know. Then I say this one now. This is the instructions. This is a brother of mine. My brothers and sisters, read the instructions. Just read them. That's where life is. And it's good. Actually, Jackson, it's good you have asked that question. Eh?
Yes.
Yeah, read the instructions. They are not a waste of time. In fact, we spend a lot of time thinking about them. Eh? And we know why we think about them. We even proofread them to check whether my email is correct, if it is my email. If it is a Blackboard link, we will put it there. We'll tell you it's in the Blackboard link, and the link will be there. Just take it there. That's where it will be. Because there's a reason. Anyway, let's not go there. Now let's go to the last thing. Eh? The last thing is now the last. Eh? But to do this, I'm going to show you where we are going with this thing. Why do we do correlation? This is the reason why. I will pick the data I have here. This one here. And to be true for any other data set on the regression. This is it. Here, X we said are advert cost. Just note that term. Y we say is the what? Is the sales volume. Before you perform any regression is basically looking back. You know, you use past data to predict the future. That's why they are called predictive models. You know, you predict. There are a number of predicting models. Eh? So you go to your lecture 1, data and statistics. You look at the levels of measurements, and there were 4. The level of measurements were nominal, ordinal, interval, and scale. That is the basis of all these things we are doing. Then you also go there in the same lecture, and then you identify the classification of variables. And there's only one major classification there which is appropriate for regression. That is dependent and independent. Dependent and independent. That you must know. So that if you are asked between X and Y, which one is dependent, which one is independent, you should know. There's no theory here. The dependent variable sometimes is called an outcome variable. It is the variable that changes when X changes. It's predicted through X. So all you need to know are the values of y and x, then build a model that can enable you to predict future values or intervening values between periods or between variables. So what do? Before you perform regression, if that you must identify, check whether your variables are only two. You only have one independent variable. In this case, we only have one independent variable, the advertisement cost, and one independent variable, the what? Which cost? Which one is this? The sales volume. If you have one independent variable, then the model you'll be developing is called a simple regression model. It is not simple because it's simple, no. It's because you only have one independent variable. But reality is not one based on one independent variable. No, sales volume movement is not affected only by advert cost. It's affected by quality of management, gender of the top management, among other things. So you may have more than one independent variable affecting why? They could be 2 and above. So if they are 2 and above, therefore you are probably x1, x2, x3, x4, x5, whatever the number. When you have more than one independent variable, then the model you'll be building is multiple regression model. If there only one independent, it is simple. If there's more, it's 2 and above, it is multiple. That's the first thing you need to note here before I put in the presentation. Then you cannot build complicated models. The best model for predicting the future, the best assumption to make is that X and Y are linearly related. That's the best. You build a linear model, knowing too well that reality is not linear. You don't get perfectly linear models. Reality will be fluctuation between X and Y. If you do a scatter plot, you'll see some fluctuation between X and Y. It's never linear. But you build the best linear model possible. The best linear model possible to estimate Y given X, whether multiple or simple. So here we'll deal with the simple. Then we will generalize for multiple. Lastly, the dependent variable. If the dependent variable is ratio, like it is here, Y is ratio. The dependent variable is ratio. The model being predicted is ratio. It is this one. These are numbers. Then the model, of course, will be multiple regression model. Note these things, note them. If this variable here, this variable is ratio, but this can be anything. Can be nominal, can be ordinal, can be ratio also. But if this one here is nominal, two-level, like gender, male and female, adoption of technology, adopt, don't adopt. You probably want to know the factors that affect adoption. 2, defective, non-defective. So if this one cannot near seem two-level, then the model you'll be building will still be a regression model, but it is not multiple. It's called logistic regression model. Logistic regression model. Because these things will be asked sometimes in future. This is also not the basis of your course anyway, but I'll tell you. If these are only 2-level, gender, adoption of innovation, defective items, etc., etc. However, if this dependent variable here can assume values between 0 and 1 inclusive, 0 and 1, why here could be efficiency. Efficiency of a firm can be expressed as a percentage, 10%, 1% efficient, up to 100%, which could be 0.1, 0.2, up to 1. So it's between 0 and 1 inclusive. So y can take any value continuously between 0 and 1 inclusive. That doesn't mean it is ordinary, it is nominal. No, it's still continuous, but it's between 0 and 1 inclusive. Then the regression model you'll be building is not multiple, is not logistic, but is called censored regression model. Censored. All these stories, you see them, you'll see them. Censored between 0 and 1 regression model. There are other names for that model. This is the third most important. So we have multiple simply, we have logistics simply, we have then censored regression model. These are the possibilities you can have in your data set. Clear? Lastly, if this variable here, which is the dependent, is ordinal, ranking, Likert scale, again, you cannot use simple regression, multiple regression. You cannot use logistic regression. You cannot use censored. But the model you'll be building is called ordinal, because it's ordinal. Ordinal, logistic regression model. So what determines the type of regression model you build is the nature of the dependent variable. The nature of the dependent variable will determine the type of regression model you build. For this course, past 62.5, nobody will bother you about logistic regression, but you need to know about them. Nobody will bother you about censored regression. You need to know about them. Ordinal, you need to. Those are PhD issues. But if you want to use them in industry, before you move to your PhD, you will hire me as a consultant, and I will take you through. Because that one you need anyway. Just talk to your organization nicely. They will come to me, single source me, and we'll deal with those issues. For now, we are going to deal only with multiple. And we are going to deal, sorry, with the normal regression. And we are only going to deal with one simple regression model. Jelly, any problem, any issue?
No.
No. Good. Now, yes, please.
Kindly repeat the point on ordinal, please.
Ordinal, you see, ordinal is when you have like Likert scale. You know, like you want to see the factors that affect quality of service. You know, you ask respondents to rate quality of service in a bank, isn't it? Then yes, they rate them on a scale of 1 to 5, isn't it? So in this case, quality of service is the dependent variable, isn't it?
Yes, yes.
But the other factors like gender of the respondent,
okay,
level of education of the respondent,
yes,
where they stay, where they come from.
okay.
You see that, So that's important. Yes. That's very important. But you need to know these things. You need to know these things, basically, somehow. Now, let's deal with the focus. And the focus is this. Before I go there, the focus is this. What is this regression line? Because a model is just a line. The first thing I want to, we are doing with the simple, where we only have one independent and one dependent. What is the general equation of a straight line?
Y is equals to mx plus c.
Y is equal to mx plus c. Those things don't change just because you're doing MBA. It's still the same. It is still y is equal to mx plus c. So you want to derive y is equal to mx plus c using this data set. But I'll tell you what we do by posting this first to take you through the process. Then I'll come back here. I'll come back here so that we sort it out nicely. So we come back here, there. Simple. Where is this thing? Here we are. So this is simple regression. And those stories I think you can read. Now this is it. This is what I was trying to say. This is what I'm trying to say here. They're all here. Your life Explanatory variable are the independent variables. You know, those are explanatory. Yeah? The outcome variable is the dependent. Eh? So this is it. If you have only one outcome variable, then it is simple, linear, or simple non-linear. This is not our life. Our life is linear. If it is more than more than two explanatory, the independent variable, we build multiple linear or multiple non-linear. Our life is not here. Our life is here. There is no, or this is for the standard regression models, not logistic, not the ordinal, not the censored. Eh? Fine? That's what I was saying. Eh? And this is it. That's the purpose. The purpose, all these stories, the purpose is basically to predict a predictive line, a line you can use to predict values into the future or between values. That's what these stories are saying here. I don't want to bog you down with this story. I want to take you to reality. Now, listen to this question very critically. And I'm only bothered about from here. Simple regression, even multiple, from here. Relationship between X and Y. You know, suppose you have Y and X as the variable, where X is independent, Y is dependent. Listen to this very clearly. You cannot use one model to predict either of the two values. That you are given Y, you can predict X. The same model, you can use it to predict X given Y. You can't. So if you are given two variables, like advert cost and sales volume, let the sales volume be Y and the sales volume be X. If you want to predict Y given X, note these things. That's number one. Note these things. If you want to predict Y given X, sales volume given advert cost, then you need to build a Y on X regression line. Please note that. You build a Y on X regression line. If you want to predict Y given X, then for given values of X, then you build a Y on X regression line. And this is it here. Y is a function of X. Y is equal to 5 of X. That means Y depend on X. This is the Y on X regression line. Here, Y is dependent, X is independent. That's number one. Number two, for the same data set, if you want to predict X given Y, you're just using the same data set. But you want to predict advertisement, what you would have invested in advertisement given a sales volume. Then you build an X on Y regression line. An X on Y regression line, which basically is generally written as X is equal to F of X. X is equal to F of Y. The reason why you do that, if you use the same model to do the two predictions, your model will be characterized by huge systemic errors. You will be introducing errors in your prediction. And these errors can be mathematically shown, the differences, the residuals, they are there. That's why you always must you must always build the two models, a Y on X, X on Y. And Excel and SPSS starter EViews gives you that option of building either of the two models for your purposes based on the objective of your study. Am I clear, please?
Yes.
Good. Now, this is basically it. This is what it is. We are looking at the relationship between correlation and regression. You know, correlation. This one I'll just show you, then I go to Excel. Let's come here. Let's come here first. Here first. Correlation. I'll pick the data set here. This data set. This one. I'll just share it now. I'll share it here. This one. Let us draw a scatter plot in SAT. A scatter plot. That one. That one. This is our scatter plot. Let me just remove this Y from here. For that one. That just means that's why it's independent. In this scatter plot, you can see X and Y are positively correlated. Are you seeing this? You're seeing this? Now, suppose I asked you, what is the value of Y for this given value of X? You will never know. Isn't it? Because this is not given. Or I go beyond here. What's the value of Y? What's the value of Y that gives us 60? You will never know because it's somewhere up here, but you can't know. The regression line will be able to enable you to predict these values beyond or these values in between. That line, which is of the form crudely, Y is equal to mx plus c, is the line that passes through most of these points. Most of them, or as near to most of them as possible. Most of them, or as near to most of them as possible. That is the regression line. It is sometimes called the line of best fit. The line of best fit, because it's the line that best fits your data. You will see in a minute that is the line that minimizes the error between itself and the actual values. It minimizes the error between itself and the actual values. If I asked you, each of you, to draw your line through this point, the best line according to your perception, I'll have as many lines as you are there, out there, you are 45. I'll have 45 different lines. But there is only one line of best fit. And that is the purpose of regression analysis, to come up with one line, one model for predicting Y values given X, or X values given Y. And that line is here. It's a line we can generate from here. The line of best fit. The line of best fit can be generated from Excel, from here. By simply clicking there, right-clicking on the, you click on there and select the points, then come to add trend line. This is in Excel, And when I add trend line, this is the line of best fit. Are you seeing this line here? You're seeing it?
What does it mean?
So this line, I can extend it down this side or and up that side. You see what it means, So now if you ask me what's the value of Y for this given of X, I just draw a line up to this line and draw this side. Or I draw here, this side and that side. Or I can extend it beyond and then I draw a point from here to there. I come this side, I read these values. So this is the line that you can use to predict values. And it has got its value, this line here, based on the data set, This line here. It has got its equation, which we are going to derive. You'll see it in a minute. No, in a minute. So we're going to derive that line. So with this line here, if I came here and I come to trend line, format trend line, you'll see what this line means in a minute. Come on, please. This is the one, and then format trend line.
It's on the right.
Where is that? That's that tab. I want to click this. I want format trend line.
It's on the right already.
Where is it? I'm not seeing it here.
On the right of the Excel.
Oh, good. Yeah, that is it. It is here. That's why it was hiding. So in a format trend line now, I add. What do I want to add? That line. What is it? What is it? Display display the equation on the chart. Are you seeing this one here? This one? Below here?
Yes.
I click this. When I do that, then I just do OK. It is here. Are you seeing this one?
Yes.
Yes.
So y is equal to mx plus c. Remember the c, that's c, eh?
Yes.
So so m is 0.64, c is 12.10 from that. That's the point, the intercept. If I brought this line all the way up to here, it will be 12.34. So when x is increases by 1 unit, 1 unit, we can get y. Y is equal to this times 1 plus that. If x is equal to 0, you don't advertise anything, then this will be the sales volume. So this is the meaning. This is the line we need to derive, this one here. We need to derive ourselves, this line here, using standard models. And that is what we are calling the line of best fit. And there's only one line of best fit. There cannot be more than one for a given data set. Is that okay, please?
Yes.
But if not, this is for y on x. Are you seeing y here? You seeing y here? If I wanted x on y here, then all I need to do is to bring this data, this one here. I'll just bring it here. If I want to x on y, then what should appear first is x. Just bring this one here.
I want x on y.
This is y on x, eh? You see y here?
Yeah.
Y a function of x, eh? Independent, eh?
Mm.
Now I want x on what? X on y, eh? So I'll just pick this. This is why I'm doing this, eh? I swap them, eh? I swap them. I swap them this way. This now will be what? This will be y, and this will be what? X. Then where is y? Where is y? Y is here. That's our y, eh? And where is x? Our x is here. That's our x, eh? Then now you can see the model we are building, eh? Then now we can create our trend line again. We can recalculate our trend line, eh? Our trend line, sorry about that. You need to rerun this, eh? To get the exact thing, eh? Where's that value there, please? I think I'm not done. Eh? This is supposed to be x, eh? This is supposed to be x, eh? That one, eh? That one. And this is supposed to be what? Supposed to be what?
Y.
Y. That is the y on x. X on y. The other one is, so now you can predict to x given y values. The sales volume, what you need to advertise on for a given sales volume. How much you need to spend on advert if you got some sales volume. That is the y, x on y regression model. This is using Excel. And this is called the line of best fit. So what is this line of best fit? You're asking me. This is how you get it now. And please, let's now go back, and that's where we will stay for some time now. Now you're seeing what it means, eh? Whoever was asking, what does it mean, eh? Okay. Now, I'll go back now, here.
And also.
Just sharing this in a minute, please. So this is it. This is where we are. So now look at now the way these are now terminologies. Eh? This is y on x. Are you seeing y on x?
Y on x.
Shared, eh? What is this symbol here? This one. What's this symbol here called?
Beta.
Beta.
Beta. Beta is the same as C. You see the intercept, eh?
Yes.
And this one is the same as what? Beta 1 is the same as what?
M.
M.
And epsilon is the same as what? This is epsilon. There are term, eh? You see what it means in a minute, eh? In a minute you will see. This is y on x. Y is the dependent, x is independent. You can see there. The same data set. This is now x on y. Are you seeing x on y?
Yes.
Which symbol is this?
Alpha.
Alpha. Alpha naught plus alpha 1 y. That's what you have just built that side. With an error term e. You'll see what it means in a minute. And just imagine Excel. So this is what this means. Let's go through there. The line we have just drawn that side is this one. It's just mute. Eh? The line we have just built is this one. Can you imagine that Excel line? Eh? It was passing through some points or generally between those points. You can imagine what it was, eh? In Excel, eh?
Yes.
The difference between this point and that point is the error term. This point and that line is that error term. This and that is the error term. This and that, depending if you had 10 points, not all of them not lying on the line, then you'll be having 10 error terms. Some of them will be above the line, some of them will be below the line. If this is the line of best fit, and you got the error terms, all of them, the differences, and you add all of them, what will they total to?
0.
0. If this is the best line, and they are therefore called random error terms. I'm explaining this line. Any point on this line, because this line is generated from data, are called predicted values of y given x. So we have x here, the predicted value will be this one. If you have x here, the predicted value will be this one. So we have predicted values. The points on the line are predicted values of y given x. If it was x model, it will be x given y. However, these actual points, these ones, are the actual data values, and they are called observed values of y given x. And the same principle is used for x on y, for x on y. The same principle. Now y is the horizontal axis, x is the vertical axis. Am I clear, please?
Yes.
Good. So what is there for this line of best fit? The line of best fit is called the estimated line. This line here, estimated. This is the line that reduces the sum of the errors to what? To what?
0.
To 0. That is the line that reduces the sum of the errors to 0. Therefore, the equation of this line will be the same equation, but without epsilon. And that will be the estimated regression line for x on y. This one here, if this is the line, then the equation of this line will be y plus beta is equal to beta naught plus beta 1 x without this. That will be the estimated line of y given x. And those are the regression lines. And these are the ones here. This is the estimated line for y on x, now denoted by y cap. Y cap is the estimated y value for given values of x. See, this x is not estimated, it is given. Beta cap is also estimated. Beta cap naught is also estimated. The same principle is true for x. It will be x cap y, x cap I is equal to alpha naught cap plus alpha 1 cap y. So the objective, the procedure for determining this regression line is called the ordinary least squares method, OLS. To determine this regression line, you deal with ordinary, you use the ordinary least square regression model. Sorry, with ordinary least squares method, OLS method, where the OLS method is to determine, enables one to determine the values of beta naught cap and beta 1 cap that minimizes the error term. The value of beta naught cap and beta 1 cap that minimizes the error term, takes error term to 0 for y on x. The value of beta naught cap plus beta 1 cap x, sorry, the value of beta naught cap and beta 1 cap that minimizes the error term. That is the OLS procedure. You use the OLS procedure to find the value of beta naught cap and the beta 1 cap that minimizes the error term. I'm repeating that. During your life as a student, which procedure have you used to determine the values of variables that, the values of independent variables that minimizes the dependent? Which procedure have you ever used in your student life? When you want to minimize the value of the dependent variable, given an independent variable, which procedure have you used before in your lifetime? How would you minimize y given x? Which procedure have you looked at in the past? Not necessarily in statistics. What have you used in the past? Anybody? Do you remember? How many of you did calculus? No, I'm not going to test you in calculus. I'm just asking. How many of you did not do calculus?
We did, but we can't remember.
Oh, you can't remember. Now that's where I've told you they follow you forever. So you better start remembering, eh? You better start, eh?
They say differentiation.
Differential calculus, optimization, stationary points, differential calculus. And that's what we are going to use here. I'm not going to subject you to differential calculus, but I'm going to give you the result. I've derived it here for you, but I'm going to give you the result of that differentiation that gives you beta naught and beta 1 that minimizes the error term. I'll show you for y on x, for y on x. So since I have two unknowns I want to determine, I want to know beta naught and beta 1, how many equations do I need to solve for two unknowns? How many equations, if I have two unknowns, how many equations do I need to solve for two unknowns?
2.
2. So I need 2 equations to enable me to find beta naught and beta 1 for y on x, or alpha naught cap and alpha 1 cap for x on y. Whatever symbol you use is relevant here, is the procedure. So I'll deal with this one first, this one. I'll just peruse through the procedure, which I've derived for you, but I'll give you the result. So this is the model here. I want the value that I want to differentiate the sum of squares with respect, this is the error, with respect to beta naught and beta 1. That's all I need to say there. Forget about the other issues using differential calculus. Then I've done this for you here, all the way done. I'm taking you to the result. All the way done, this for beta naught and beta 1, all the way, I'm taking you to the result, eh? To the result, eh? So the 2 equations I need to solve for beta naught and beta 1 that minimizes the error term based on this derivation here, which you don't need to bother about, is this one. That is the equation, this one. To find beta naught cap and beta 1 cap for a given data set, you solve for two simultaneous equations. These two simultaneous equations are the ordinary least squares equations, sometimes called normal equations for y on x. And I've gotten them from this derivation here, which if you're mathematical, you can go and check. If you're non-mathematical, don't bother. Just peruse, and then you go come here. This is where I was coming to. So this is sigma xy is equal to beta naught cap sigma x plus beta 1 up sigma x squared. The next equation is sigma y is equal to n beta naught cap plus beta 1 cap plus sigma x. The unknowns here are beta naught and beta 1. That's what you don't know. That's what you want to find. Because we have x values and y values. We know n. This is for y on x. The x on y normal equations is the mirror image of this equation. It is the same. It's the same, the x on y. If you want to determine the x on y regression line, we'll use the normal equation, which is basically a mirror image of this one. So can somebody out there tell me how would the normal equations for x on y look like? Because this is for y on x. What will the first equation for x on y?
The first equation would be
yes,
sigma yx equals alpha cap naught sigma y plus alpha 1 alpha cap 1 sigma y squared.
Sigma y squared. You know x, y, yx, it doesn't matter what you sub, how you isn't it? That doesn't change, isn't it? Because x times y is the same as y times x, isn't it? That's fine, that's good. Then the second one is what?
The second one is sigma x.
Sigma x
equals n alpha cap naught.
Alpha naught cap, yes.
Plus alpha 1 cap sigma
plus
y.
alpha 1 cap plus what?
Sigma y.
Sigma y. That is it. That's the normal equation for x on y. The rest of the things now are standard. So I want us to use our data set to deal with, to find x on y and y on x. X on y and y on x. The same data set I have that side, eh? The same data set, eh? I'll come that side where we were. Go to Excel. Go to Excel here. Then I paste this one here. This is the y on x. I'll share. That is the y on x. Eh? I'll revert to what these things were before, eh? So that we come up. It doesn't matter really where we are, but I'll just use the same data set. Let's use the same data set, eh? But I want us to use what we had before, really, so that we. But it doesn't matter. Does it matter really? No, it doesn't matter. So this is it. I want to delete the other one, eh? So that we are clear what we are doing, eh? Please put your a pen aside, eh? And paper, so that you see what we are doing, eh? You can take some little notes, eh? I want to determine y on x line, eh? The y on x line, which is equal to y is equal to beta naught cap plus beta 1 cap x. That's what I want to determine. Y on x. So y on x, it is here. You need a column called, the first equation, you need a column called sigma what? Sigma what?
XY.
XY. So I need XY here. Then, and that's it, isn't it? They need X what? What's another column you need here? You see this?
X squared.
X squared. And that's it. So I need XY, which is just this, times that. And I need X squared, which is just this. That's it. Then I copy everywhere. Everywhere. That's it. What do I do with those things? All of them.
Sum.
You sum all of them. Please, now this one I'm telling you, take your note and paper. You know, you need to note, just write the sums I'm giving you. So write this, sigma y is equal to 496, this one. This one, sigma y, write it please. Sigma y is equal to 496?
476.
476, right, 476. Sigma xy is equal to 473.
Sigma x.
Sorry, sigma x is equal to 473, sorry, 473. Fine. Sigma xy is 201173. Then sigma x squared is 201137. 21137. The other one is 21173. This one is 21137. You got that?
Yes.
So write the following now. Please write the following. Equation 1. Write them now. From this equation here, right? Where is this? 21173 equals to 473 beta 1 cap equals to 473 beta 1 cap.
Beta naught.
Beta naught cap, sorry, beta naught cap. Plus 21137 beta 1 cap. 21137 beta 1 cap. Have you done that, please?
Yes.
That's equation. Label that as equation 1. Below it, you write 476 equals to, what is n in this problem?
13.
13 beta naught cap plus 473 beta 1 cap. 473 beta 1 cap. Are we done that, please?
Yes.
Good.
Yeah.
Label that as equation 2. You see me, I don't want to go to word 2, start making this aesthetics here. So now you can, what is the unknown there? What are the unknowns there?
Beta naught cap and beta 1.
Beta naught cap and beta 1 cap, isn't it?
Yes.
And there are two simultaneous equations, aren't they?
They are.
How many methods do you know for solving simultaneous equations? Give me the one. Give me not two. Elimination.
Simultaneous.
What do you mean simultaneous?
Oh, graphical.
Graphical. Substitution. Which other one? That's the thinking capacity gone, isn't it? And the matrix algebra.
Oh, yes.
Oh, yes. Which one is the easiest here? Which is the easiest for you here?
Substitution.
Substitution. Good. So what are you going to, which equation are you going to use to substitute? Which is the easiest equation to use?
The second one.
The second one, isn't it? So write this from equation 2. From equation 2. 13 beta naught cap. From this equation here, 13 beta naught cap equals to 476 minus 473 beta 1 cap. Are you seeing where that one has come from?
Yes.
You're seeing where that one has come from? So what is beta? Therefore, beta naught equals to what? Do beta naught. What's beta naught equal to? What do you do?
Divide by 13.
Divide everywhere by 13. What do you get? Give us the result, please. Beta naught is equal to what? So you add 476 by 13, is it?
36.6.
You also divide what by 13?
473 divided by 13.
Good.
36.4.
That's all right. That beta naught equals to 36.6 minus 36.4 beta 1. 36.6 minus 36.4 beta 1. Is that okay?
Yes.
Is that okay, everybody, please?
Yes, yes.
Label that as equation 3. You done that?
Yes.
Then write the substituting for beta naught cap. Substituting for beta naught cap in equation 3. Sorry, from equation 3. In equation 1. You substitute for beta naught cap from equation 3 in equation 1. What do you have? What is the result? Let's substitute. 211.73 equals to. Are we done? Are we writing?
Yes.
211.73 equal to 473 bracket 36.6 minus 36.4 beta 1 cap bracket. I'll repeat. 211.73 equals to 473 into 36.6 minus 36.4 beta 1 cap bracket. Is that clear? You know what it's doing there?
Yes.
I've just put in beta naught, eh?
Yes.
Plus, plus what? Plus the other term, isn't it?
Yes.
And what's that time? 211.37 beta 1 cap. That's it. So let's simplify. Equals to, now you multiply 470, whatever. What is it you multiplying inside? 473 inside, eh? What do you get? Remove the bracket, eh?
17,311.8.
17,311.311. Just to call it 17,319. Isn't it?
17,312.
Yeah, because of rounding, eh?
Yes.
Because of rounding. Just remove the bracket and give me the result after you remove the bracket, eh? What do you get? Just remove the bracket in the first term. The other one is fine. So that's what you get. You should get, what is it called? What's sigma xy? You should get this, eh? You should get 211.73 equals to 17,319. Let's use that, eh? Minus 17,211 beta 1 minus 17,211 beta 1 plus what? 211.37 beta 1. Is that clear? One, I just move the bracket. The other one, the term is there anyway. So this is the final result there. This is the final result, eh? The final result is as follows, right? The final result, eh? Therefore, 211.73 211.73 equals to 211.73 equals to 1739 plus 3927.08 plus this one, beta 1, plus 3927.08 beta 1 cap. That's the final result. It is this one plus 3927 beta 1. Now solve for beta 1. Now you solve for beta 1. So write this, the following. I'll just write it for you. 3927.08 beta 1 cap. I'm writing it for you. 3927.08 beta cap equals to 211.73. I want to put like times together. 211.73 minus 1713.08, or what? What's just 17,319 minus 17,319. So it is this 211 minus this. So beta 1 cap, sorry, 3927.08 beta 1 cap equals to 211.73 minus 17,319. Therefore, beta 1 cap, that is the result. Beta 1 cap equals, I'll give you the result now. Beta 1 equals to, I'll do that, is equal to 3853.9. 3853.9 divided by 3927.08. 3953.9, this one here, 3953.9 divided by 39.27, or to 3927.08, which is equal to this divided by that, which is 0.98. Beta 1 cap is equal to 0.981. Beta 1 cap is equal to 0.981. You label that as equation 4. Beta 1 cap equals to 0.981, 0.981, which is equation 4. Equation 4. Lastly, substituting equation 4. Substituting equation 4 in equation 3 for beta 1. Substituting equation 4 in equation 3 for beta 1. What was equation 3?
Beta naught cap is equals to 36.6 minus 36.4 beta.
Now put, wherever there is beta 1 cap, put this value. So what is it equal to? Just tell me. What's equal to what? Just give me the first value. What you're multiplying by beta 1?
36.4.
36.4. So it was what? 36.69, eh?
6.6 minus.
Minus this value, eh?
Yeah.
Minus this value. That is beta 1. No. This 36.6 minus this one is 0.908. Is that okay? So write this, that beta naught cap is equal to 0.908. You can solve that, eh? Beta naught cap is equal to 0.906 for that matter. And I want you to note those things, eh? Note them. Beta naught cap is equal to 0.906. 906, eh? Just note that, because there's some statement I want to make. There's a statement I want to make. So, look at what I'm doing here. Look at what I'm doing here. I want us to do a scatter plot. I start again. Now we want to relate these things. I start again. Here we are. This is the scatter plot. No, sorry, boy. Here, I insert the scatter plot for the data set. There we are. This, then I insert a trend line. I insert a trend line. Come here. Then do that. Then format a trend line. No. That's, come on, please. I'm going to deal with it just now, so that you see it clearly. That's it. Then insert a trend line. Then I add the line. Display the equation. And here we are. Are you seeing this one here? This one?
Yes.
Why are they different from what you have gotten here? Why are they different? Why is this one's different? Because this one we have got 0.908, isn't it? And the other one we got what?
0.985.
98 something. Is it, why are they different? Where is the difference? The procedure is the same, The problem is probably in our count or substitutions, Not even substitution. Rounding, That one you need to confirm, Is that okay? This the line we should be getting is this one. These values are supposed to be equal to these values. I wish I was using it this side. We would have gotten the correct thing if I was seeing them here. So just check that, that these values, this one, this 0.908 here is actually the one we are seeing here. This one here, is this positive or negative? This one?
Positive.
Positive. This one here is the one which is supposed to be this one. But this line is clear. I cannot predict X values given Y value given X. I can ask you, what is the sales volume if I spent 100,000 or $1 million? I simply put 100 million here. Then I multiply, I get my Y. What would be the sales volume if I spent, say, 45 million shillings? Here, I would just substitute, put 45, and I get my Y. That's what they call predictive models. Predictive models. So you can go and repeat this, and check whether you're getting the same result, Is that okay? Now, quickly, very quickly. I can also use Excel, this one, data pack. You see this, Here. Then, regression. Regression. Is here. Then I come here. Then I define my X range. Y range, it is this one. I define my X range, it is this one. Then I come and now put the label. The first row are, of course, labels. I'm going to assume that there is no intercept. You don't have to bother about this. I want a confidence interval that I will find the line between something. I can click here. The default normally is 95% confidence interval or 5% level of significance. That you need to always click. It has meaning. These are other things we need to get, especially for multiple regression. But for this one, I'm not going to complicate it. I simply run my regression. And this is the result. Look at what I've gotten here, please. Look at this output. This is the output. We were right. Are you seeing this one? Are you seeing this?
Yes.
We were right, incidentally. The other one, I think we were doing X, the data set. I swapped the data set. That's why. That's why. But we were right anyway. So this is okay. This is okay. Forget about this ones here have meaning, this ones here have meaning, this one here has meaning, especially when you deal with the multiple regression, and this of course at the level are the confidence intervals. This what's important for you here is this R squared. This R squared for this data set. Look at this. Are you seeing this R square here? This one, eh? This one. What's the value here? If you're reading.
0.998.
Beautiful. For this data set, we got some R, the Carl Pearson, eh? The Carl Pearson, eh? The small r, eh? R square is the square of Carl Pearson's. In fact, R squared is R, small r squared. That's what I will tell you to use small r, because this is a different thing. R squared is the square of Carl Pearson's, and it is called the coefficient of determination. The coefficient of determination. The higher the coefficient of determination, the better the line. The higher the coefficient of determination, the better the line. In fact, if R square is equal to 1, then all the points will lie on a straight line. Otherwise, they'll be far away from the line of best fit. So you need a higher coefficient of determination. A higher coefficient of determination. It is the power of your regression line. That's what it is. For this one here, this is for multiple regression. This one. You only use this for multiple. This is for simple regression. For simple regression. And the way you interpret this, if you use this, then this is also just significant for multiple regression. ANOVA table, analysis of variance table, which of course is in multiple regression, which I said we'll only deal with when we are in through SPSS, through SPSS at one point. But this is the output. So now you can write your regression equation from either from what our calculation or just from the line, like this one here, this one. Ours, I'll bring it here. I'll just bring it for you. I'll bring it for you. Our general equation was this. This is the estimated equation, not the general one. This is the estimated equation. The estimated. This one. So after you have made your calculations, then now you have to substitute them here. Now you will say, you will come here and say, what is beta naught? What is beta naught here? Can somebody read it? What's beta naught cap? What is it here? I was 0.908, the intercept, eh?
Yes.
Good. 0.908. What's beta 1 equal to?
0.981.
0.981. Those things we got, eh? 0.981. Just put it here. Put it here. .981 x, and that is your estimated regression line. That is your estimated regression line. You substitute those values in there, you get your estimated. This one is cumbersome because I'm using other things, but this is it. I'll go back here and I'll show it to you how it looks like when you substitute. Now you write your line, eh? This is how it looks like. This is how it looks like. I'll go here and I'll show it to you. Show it to you. How you substitute them. Was our example here, illustrative example, which is here. Building the model for about those ones. I've built a model here for you through an example. Eh? This one. The model here, regression model. This is the model, the same as what I've just posted that side. We want to, this model was to determine a line for actual selling price and the house size. Eh? Here was that the selling price was influenced by the house size. Then we build a model here. This is the procedure, and I went on and on. I determined the beta naught, I determined the beta 1. Then I came up with my line here, the line here. The values are here. Beta naught is equal to 9.096. Beta 1 is equal to some value here, 10.714. So that when I come this side, I build my line. The line here will be now, just notice 9.091, and this one here is here. Y cap is equal to 9.096 plus 10.714x. Why? Because my general line was this one. This one. Also substitute for beta naught and beta 1, and you got your predictive line, which of course I've related to Excel also here. How to interpret Excel? This one here is beta naught, this one here is beta 1. Of course, you have R there, and you have other measurements there. And that's it. So in the example here, in this example, this one, where is it? The data. In this data set here, I want you to go and derive the X on Y line. X on Y regression line. X on Y.
We're still on PowerPoint.
Oh, sorry. I want to go and derive X on Y line. This one. X on Y line. And determine, you remember X was the advertisement cost, eh? And determine the advertisement cost if the sales volume is 80 shillings, because could be millions, is 80 shillings, and hence determine the advertisement cost given a sales volume of 80 shillings, probably in millions, 80 million shillings. Man, these are reduced to figure, it will just be 80 million shillings. You don't use 80 million, you use 80, because even these ones were in millions anyway. The scale. So that is the regression equation. Please do that. Please do that. Any question, please. Any question? Now that is what we have done to date. The rest we'll deal with in SPSS. In SPSS. Yes, Augusta.
Excuse me, sir. I'd like clarification, but not for this topic.
And let's deal with this one here first. Any question here? Okay, go on.
Okay, so it's on hypothesis when you're doing the t-test and the z-test. I wanted to be sure which approach you want us to use, because we have the population approach and we have the standard deviation approach. So what do you want us to look at? Do you want us to look at the sample size or the standard deviation of the population? Which do you recommend?
What do you mean? You know there is only one standard deviation, eh? You know, you will not have the population standard deviation, eh? We said that when you're doing estimation, that you use the sample standard deviation to estimate for sigma, the population standard deviation, eh? So they'll not be different. You will use one to estimate the other, eh? So whether you use sigma or you use S is basically not an issue. I know that's what you're asking, isn't it?
I'm asking
yes.
Which approach should we use? Should we look at the sample size, whether it's greater than 30 or less than 30?
Of course, the sample size. Oh, it is the sample size. Oh, yes. Okay. Oh, yeah. It is the sample size you're dealing with here. Eh? Greater than or equal to 30, yeah?
We ignore the population, whether it's S or the other sigma. That doesn't matter. We just look at the sample size.
I'm saying the sample size only becomes significant when you are dealing with normality or T, eh?
Yes.
When n is less than 30, you assume normality, 30 and above,
Okay.
When it is below, it is small, It is t.
Okay.
Isn't it? But therein, whenever you, because now what you'll be using, you'll be having your sample data, So that sample data you're using to collect, to determine some standard deviation,
Yes.
To estimate sigma, the population standard deviation, Then you proceed and use your standard deviation estimated from the sample.
Okay.
Yes.
And where does n-1 come in?
N-1, I said, N-1, I said that in most, if you see that in most texts, you find that if the sample size is small, you do a correction with n to n-1, when you're calculating t, isn't it? But for me, I said that to me that is semantic, That's semantic when you're doing your calculations, Simply use n. Even if you use n-1, the differences will be very minimal. You see, if you are dividing by 90, then you divide by 98. It's not much difference, isn't it? Your conclusions will still be the same. Those are basically corrections we make in statistics. So whether you use n-1 or n, to me is inconsequential, because these mathematical issues. Either way, it doesn't matter to me. Yeah.
Okay, so we can use whichever, and you'll consider that when marking.
What have I said, surely? I mean, what have I said? You know me, I'm not, I'm very clear. Why are you repeating to me? Marking what? Are you sure it will come? My sister. Well, you're asking me whether, you're actually just telling me that it's in the exam. It is not there, Because if I told you it yes, then it means it is there, isn't it? And if I deny also, it's the same. But rest assured, Augusta, that it doesn't matter. You can use n-1 or n. It is inconsequential, especially when you're calculating these things, because there's minimal difference, in terms of the result. Any other question, please? Any other question? Good. If there's no other question, that's where we stop. And then we agreed that you arrange, then we'll deal with SPSS, and they arrange it after the exam. That will be between you and me, and then we move on. So now the exam. We are there?
Yes, we are there.
Good. Exam. What did we do up to midpoint, midterm, mid-semester? What did we cover up to mid-semester? Because I wanted to come from you,
Voice 1.
Up to mid-semester,
Normal.
No more. We did up to distributions, isn't it?
Yes.
Yes.
Good. Good. So your exam is the same standard 3 questions. Question 1 is compulsory. Is that okay?
Yes.
And the exam basically will include everything, including estimation. No, not these things, not them. Sampling, distribution, and estimation. That's number 1.
Sorry?
Jackson, sampling, distribution, and estimation. That sampling, distribution, estimation. No, there's no theory here. Because, sampling, distribution, and estimation. That's number 1. Number 2, I'm just giving general topics,
Yeah.
Hypothesis testing. Number 3, correlation and regression. So you are done?
Yes.
Beautiful. But please read instructions clearly. So wish you luck, and then we will, I'm available if you want to consult, please do. I'll be available. We can do a Zoom, at a convenient time. If you want some clarifications, that's not a problem. You can just create appropriate time. Exam.
How soon are we getting the recording for this class?
This one must record,
How soon are we getting?
I don't know, probably tomorrow, eh? Because I'll move from here, it will record, then I will send to you, eh? But let's deal with it tomorrow, eh?
Okay.
Yes, please. Sir, register.
Mwalimu, a suggestion.
Yes, please.
I don't know whether the class is in agreement. Since as it stands right now, we are used to these Tuesday classes.
Yes.
So before we forget many things, perhaps maybe after the exam, if we could just schedule the next Tuesday after exam to do the SPSS and data review before the schedules change.
That would be fine with me incidentally. That would be very fine with me. There'll be no major change, eh? It's just good to do these things immediately, eh? So let's just agree that after the exam, do the first Tuesday, we'll deal with SPSS, eh?
Yes.
Okay. And of course we have data. We will use anyway. So there's no hassle, there's no major. We just use the other data, the small data we had, eh? To illustrate that the process all through. I think let's do that. Thanks a lot, Robert. Let's do it the immediate Tuesday after that, eh? And I think Tuesday is good for everybody this evening, eh? Rather than doing another day. I think that is fine. I'm agreeable, I'll be available.
Prof, if we miss that one, is it okay? I had planned to be in the village.
You know, when you miss, you miss, you're at home, eh? You're at home with that one, isn't it? Yeah, if you're at home, you're at home. No, not being at home. I'm saying you're at home with SPSS, eh? That's what I mean. But let me ask you, Wilson, let me ask you.
Yes.
I teach, where is your village? Where is your village? Which village is that where you have no power? You have no this man. Don't use that as the next, which village? Which village are you talking about?
In Kitale.
No. Kitale, what do you mean Kitale? Let's do SPSS where in Kitale. Please attend, please just attend, my brother, attend. Go under a tree, put on your laptop, and then attend. You can get the Safaricom, what is it called? MiFi, eh? It is good. You know, it's just buy. Then you leave.
I will try.
You try. I know Kitale. Even today I was zooming from Kitale on a curriculum issue. And this one was using a phone. He's in Kitale, actually, with the family. So he still claims he's locked in Kitale. I don't know which country he is in, but he can't come to Nairobi, so I don't know. But let you try to join us when you are there. If you fail, to join, then there is a class which is the Saturday class, eh? Saturday class, eh? Which has a class from 1:30. That's even more. It will be more of a challenge for you, eh? 1:30 on Saturday, eh? You know, you can come and attend, but I would rather you attend this one, the Tuesday one. Eh? Just try, and you never know. You may be able to just come in. Yeah, please register. Susan, yes.
Prof, I just want to remind my classmates about the assignment. It's due on the same day of the exam. So you send before you do the exam.
Beautiful.
You send
that is now leadership.
You send to the lecturer's email before you do the exam, please.
That is now leadership. And send it to my email. In fact, I would rather you send it on the same day, eh? Same day, isn't it? Same day before you do the exam. You'll have a lot of challenges. A lot of challenges if you now start mixing these things, eh? Just send it before you do the exam. And then we will be okay. That is, thanks a lot. Thanks a lot for that. Because you see, if you don't submit it, after that we'll be gone. You know, after the semester ends, people are now running around. Eh?
Yes, the village in Italy.
Everywhere. Just waiting for that makeup for SPSS. So if you don't submit it, you know, you'll just be shouting outside there. You don't even know you don't know me physically. You meet me in town, you don't even know me. You know, if you knew me, you can bash me. But since we meet in town, there's nothing you say because you don't know the person you're dealing with. So submit assignment, actually as requested by our brother. So that's it. I'm compiling what I'm doing now is compiling all your results, all of them, except that assignment. I'm on the stage of I've done with your first group assignment. Let's be clear here, really. The first group assignment which you did as a group in Blackboard, that was the first one, isn't it?
Yes.
It's good to be clear. How many of you did not take that group assignment?
There are those who joined late. I would like them to talk.
Please.
There are those who joined the class late, please.
Yes, this is important because there are gaps. If you did not do those group assignments, there are few.
Hilda, did you do the first group assignment? I guess not.
But you know they are quiet.
No.
They are quiet, my brother. Why are you waking up and sleeping, giant? These things I'm asking, they have impact. So if you did not take the first group assignment, send me an email.
Okay.
Send me an email. Let's just leave it at that. So that if there are gaps, we'll know what we'll deal with those gaps. That's the group assignment. The second assignment was a group assignment, the one you submitted during exam, the mid-semester, isn't it?
All right.
That one, everybody was there. Is that true? There's nobody who missed. If you didn't sign with your group, then that's where the challenge is. Then the last assignment now is this individual one you are submitting, isn't it? Is it?
Yes.
That's it. So please, let's be clear about that so that all of us are clear. Send me an email indicating that you are not in the group, so you did not take the first group assignment. If you did, then your marks are in the blackboard, and that's not an issue.
There was one we did on Blackboard.
That's what I'm talking about. That's what I'm talking about. Did you do two on the blackboard? Two. Just one, isn't it?
Yeah.
That's it. So you have 3 assignments, and then you have got the mid-semester, and then until 2 assignments were group. One of them is individual, the last one is submitting, then the mid-semester, and the final exam. That is it. There's no other one. Just do me an email, please. And then we'll be clearer. We'll know what to do from there. So please sign in. Sign in, please. Sign in, please. Anybody who has not gotten the mid-semester now? Anybody? Everybody has a mid-semester result. That's fine.
I believe that. All right.
Thanks a lot. Thanks a lot, please.
Prof, one more question before you go.
Yes, I'm here.
I just wanted to ask, does the hypothesis testing also include chi-square?
Where's Nani? Can you?
Yes.
Can you read clearly what I said, what the test covers?
You said sampling, distribution, and estimation.
Number 1.
Then 2, hypothesis testing.
Number 3,
correlation and regression.
Is it covered? The question is it covered?
Yes, because it is under one.
Discuss with her quietly, Don't, please.
All right.
Yeah, call your sister. Just call your sister.
Okay.
I don't know why there's a lot of capacity inside here. A lot of capacity. Even within your groups, there are a lot of capacity. Just consult inside there. You will know that you are covered fully, very fully covered.
Do you still need a CAM scan?
Do
you still need a CAM scan? Will it be handwritten?
It will not be. Will it be based on the responders? I think it will be responders, just like last time.
Last time it was handwritten for the midterm.
Prof, maybe you can shed a light.
You can use responders when you handwrite,
No.
You can use it, You can,
Okay.
Eh?
Responders is better when you're
Typing.
typing into the
The
program.
issue is typing and doing Excel.
Yes. So that's it. Other exams you use responders, isn't it? Responders is basically responders, isn't it?
Responders is hearing.
So just do the exam the way we have done the exam, eh? Then you're fine, yeah.
That will be okay.
Read the instructions clearly, eh? Read what? The instructions, eh? And I'll send it earlier. Just remind me, Kanye, I'll send you the instructions, eh?
Sure.
So that everybody is clear how we are going, eh?
Yes.
Okay, sawa then. Asanteni sana.
Asante, have a nice evening.
And please, tomorrow remind me, I will send this. In fact, let me, because this time, I think probably I'll even send this today, yeah? If the recording is over.
You need to upload it on YouTube.
Please do, Prof. We really appreciate it. Thank you.
No problem. Thanks, eh?
Good night.
And to you, same to you.
Bye.
Bye-bye. Register and then leave, eh? Bye.
Yes.